Over the last 40 years, global agricultural production has more than doubled, although cropland has increased by only 12%. This result can be largely credited to increased reliance on irrigation. Because irrigation is one of the most important cropland measures, accurate information about the location and extent of irrigation is fundamental to many aspects of sustainable water resource management. However, the extent and distribution of irrigated areas on a global scale remain highly uncertain. The possibility of mapping the distribution of irrigated areas can be actualized through the use of remote sensing satellites. Remote sensing satellites collect data about the Earth's surface by using reflected light to detect electromagnetic energy on the Earth's surface. This data is then transmitted, received, and processed into an image by identifying specific spatial, spectral, temporal, and radiometric resolution parameters. Classifying a satellite image involves interpreting those images by grouping each image pixel value into meaningful categories or classes. Producing a classified land area map provides an understandable visualization of specific information about an area's surface. In order to produce a classified satellite image, training points, which identify each desired land area type, are collected and used to create a signature for each desired class. These are used to guide the classifier on how to identify each pixel given by the satellite, based on the reference signatures. Google Earth Engine, a platform which allows users to run algorithms on georeference imagery in order to compute complex spatial analysis on satellite datasets, provides a multitude of classifiers which aid in running classifications depending on how one is aiming to classify an image. However, studies that have used remote sensing to classify irrigated lands remain relatively rare due to the complexity of mapping land use as opposed to land cover. Because remote sensors collect information on many land surface characteristics, they do not necessarily provide accurate information on how that land is used by humans. In this case, identifying irrigated versus rain-fed croplands requires information in addition to land cover class types. For this, gathering information on what type of crops are irrigated, what the distribution of rainfall in the area looks like, and what the overall trend in plant greenness and water content looks like can be useful. For instance, in regions where there is limited precipitation during the growing season, increased plant greenness and water content can generally be attributed to irrigation. The Normalized Difference Vegetation Index, or NDVI, is used to quantify vegetation greenness through calculating the ratio between near-infrared light and red light, where 0 represents minimal or no greenness and 1 represents maximum greenness. If performed accurately, remote sensing can offer useful spatial information on the exact locations of irrigated lands, which is important for assessing irrigation performance, quantifying environmental impact, and understanding changes where irrigation occurs. Gathering informational aspects such as these could be particularly beneficial in regards to the Lake Ermia Basin, where irrigation activity is prominent, which is why this is the chosen region for our study. The Lake Ermia Basin, located in northwest Iran, relies heavily on irrigation systems. However, the use of river-fed irrigation canals and groundwater-supplied pressure systems has caused the basin to shrink in recent years. The loss of lake area has diminished the productivity of surrounding agricultural lands and caused substantial economic losses. The purpose of this study is to map out the extent and distribution of irrigated croplands surrounding this region. 2 land use land cover maps were created for October 2018 to April 2019 using Landsat 8 and Sentinel-2 satellite image datasets at 30-meter and 10-meter spatial resolutions respectively. Initially, true color and false color composites of the area were produced in order to extract mean red and near-infrared band values used to calculate NDVI and identify irrigated land area. For this study, a pixel-based supervised classification was performed using the Random Forest classifier. The Random Forest classifier combines output from multiple decision trees, which are built using training data and used to determine classification criteria to determine the appropriate class label. Random Forest classifications were run for both Landsat 8 and Sentinel-2 datasets to compare accuracy results. A total of 6 land use land cover classes were identified: water, mountain, forest, built structure, irrigated cropland, and rain-fed cropland. The ability to produce land use maps which illustrate the overall distribution of irrigated croplands, such as these, objectively hope to bring further understanding of environmental impacts as a result of irrigated agricultural practices.